we listen to Sveltana Mintova, who is Director of Research in the Laboratoire de Catalyse et Spectrochimie at the University of Caen, and she's specialist of materials and catalysis as well, and in particular, she will talk about nano-zeolites today.
Good afternoon, ladies and gentlemen. First of all, I would like to thank Professor Sanchez for inviting me to be here and for the excellent logistic. Today, I will be talking about nano-size zeolites. For this diverse audience, I will start with the definition of zeolites. Zeolites are crystalline aluminosilicates with well-defined pores in the range of 0.4 to 2 nanometers. For example, 1 gram of zeolite has a pore length of 600 million kilometers, while the distance between the Sun and the Earth is only 150 million kilometers. This implies that the total length of the channels of 1 gram zeolite is 4 times longer than the distance between the Earth and the Sun. Another curiosity is that zeolites have high specific surface area if we do not compete with MOF materials. The specific surface area is in the range of 300–900 square meter per grams, which is about 100 times more than the specific surface area of natural cotton. Due to all these properties, including tunable chemical composition, high thermal and mechanical stability, zeolites find great application in catalysis, gas separation, and ion exchange processes. But today, I will be talking only for nano-size zeolites. Why we are interested in nano-size zeolites? Because the driving force for many processes, as you know, is the local environment of atoms which are exposed at the solid surface in comparison to that in the bulk. Therefore, we are trying to increase the number of the surface atom in the solids, and this could be achieved via decreasing the size of the particles or via creating open pore network within the bulk particles. If we combine these two approaches, we end up with nano-size zeolites. Nano-size zeolites have small particle sizes, but also they have well-developed pore network. Currently, there are about 239 different zeolite types available. But from these 239 types zeolites, we could synthesize only 24 with nano-size dimensions. As nano-size zeolites, we would consider all crystals with sizes smaller than 200 nanometers. Why we would like to go to these very small particles, decreasing the size from micron to nano-size dimensions? Because via decreasing the size of the crystals, substantially we could decrease the diffusion length, and thus we could reduce the mass transport limitations. Also, we could think about performing catalysis of bulky molecules at the external surface area of zeolites. Via decreasing the size of the crystals, also we could avoid unwanted secondary reaction and cold formations. The classical methods for preparation of nano-size zeolites rely on the use of organic structural directing agents. Via using tetraalkyl ammonium cations, such as tetraethyl methyl propyl ammonium hydroxide, we are able to synthesize 24 nano-zeolites. But a big disadvantage is the very low crystalline yield, which is in the range of 2–25 weight%. Therefore, during the last 10 years, we focus our attention on the so-called old-fashioned healthy food, which means we try completely or partially to replace these organic templates with inorganic cations such as sodium, potassium, lithium, cesium, etc. Currently, we could synthesize 8 nanozeolites with high crystalline yield in the range of 65 to 90%, which is comparable to commercial production of zeolite. And also these materials have high crystallinity, high porosity, and no organic structural directing agent was applied at all. Almost 20 years ago, we were very much fascinated from the nano-sized zeolite synthesized from clear precursor solution in the presence of organic structural directing agent. We learned that the most important for preparation of nano-sized zeolite is to select the initial materials and to be able to prepare clear precursor suspension, and this clear precursor suspension to be subjected to hydrothermal treatment at very low temperature below 100 Celsius. Also, we had to decrease the time of crystallization in order to avoid the Ostwald ripening and the formation of big crystals. And via changing the conventional heating with microwave irradiation, we've been able to synthesize extremely small micron-sized particles with homogeneous particle size distribution. From this study, we learned that at the same time, we have to consider both the chemical and the physical parameters. As you know, organic templates are very useful. They have many advantages, such as stabilizing very open structures, giving the possibility to prepare pure siliceous materials or high siliceous materials. They lead to formation of small and homogeneous crystals. They have high external surface area, but all these advantages come with disadvantages. As disadvantages, I have to mention that always post-synthesis treatment is required, such as calcination, extraction, or cleaving. And this post-synthesis treatment lead in most of the cases to aluminum release or partial collapse of the structure. And of course, using organic structural directing agents, always we have to connect with environmental issues and increase of production cost. Therefore, during the last several years, we try completely to replace the organic structural directing agents with inorganic cation. And this is the first example how 18-chrome 6-ether, classically used for synthesis of EMT-type zeolite, was replaced with sodium hydroxide. The key point here is to stabilize water-clear precursor suspension, highly supersaturated, but not with organic template, only with inorganic cations, and under very mild synthesis conditions, such as 36-degree heating for 36 hours, we've been able to transform this water-clear solution containing amorphous particles into EMT nanocrystals. Under high-resolution TEM, these particles appear as perfect hexagonal crystals. The size is around 10 to 15 nanometers, and the thickness is around 2 to 3 nanometers. Via replacing the conventional heating with microwave irradiation, also we were able to increase the size of the crystals up to 70 nanometers, but also we increased substantially the crystalline yield, which is above 65%. Similar approach was applied toward preparation of fauxezide nanocrystals. As you know, fauxezide is extremely important material, especially for FCC catalysts. Therefore, here the task was to be able to synthesize ultra-small fauxezide nanoparticles in the presence of sodium hydroxide only. As a result, we obtain crystals which are individual, not agglomerated, and these crystals exhibit extremely high microporosity. This is the first example demonstrating that via decreasing the size of the crystals, we do not decrease the micropore volume if we ensure high crystallinity of the materials. The micropore volume of these ultra-small nanoparticles is 0.3 cubic centimeter per gram, which is comparable with the theoretically predicted for fauxezide zeolite. In addition to that, these nanoparticles, due to the close packing during drying, form the so-called textural mesoporosity, and the size of these pores is in the range of 10-50 nanometers. Very recently, also, we were surprised that these nanoparticles are flexible. They allow xenon to go not only in the super cages, but also in the open sodalite cages, which are located at the external surface of zeolite nanoparticles. And this is one example how via decreasing the size of the crystals, we could bring new properties of well-known materials. In this case, the nano-size fauxezide with 10 nanometer size was compared with the classical micron-size fauxezide, and we have seen that in the micron-size fauxezide, no matter how we perform the xenon NMR investigation, we could see only one peak, and this peak is associated with penetration of xenon in the supercage, while at certain conditions, we could see that the xenon is penetrating the sodalite. Here is given an example how are appearing fauxezide nanocrystals synthesized 20 years ago in the presence of organic template in comparison with the nanocrystals synthesized free of organic template just in the presence of sodium. As you could see, we were able to decrease the size from 40 to 10 nanometers. We were able to increase the crystalline yield from 2% to 65%, and also the crystals synthesized free of organic structural directing agents have better micropore volume, and the lower micropore volume for the templated crystals we explain with the partial collapse of the crystalline structure during calcination. Currently, our interest is in the synthesis of small pore nanozeolites via the green synthesis approaches using only inorganic cations such as cesium, lithium, potassium, etc. Why we are interested in small pore nanozeolites? One example is RHO zeolite. RHO zeolite has a very large cavities with size of 11.1 angstrom, but at the same time it has pore limiting diameter, and this pore limiting diameter could vary depending on the cation we put in the double 8 rings or single 8 rings. Though this is a possibility to prepare highly selective materials which are able to separate molecules very similar in size, such as nitrogen and hydrogen, CO2, methane, etc. And these are some of the examples where we demonstrate that Chabazite raw zeolite with high stability up to 650 degrees could be prepared just by replacing the organic template with cesium. Several times during my presentation, I mentioned that a great advantage of nanozeolite is the high external surface area. But this comes also with a disadvantage. Via preparing nanoparticles with well-developed external surface area, also we bring a lot of defects in the structure. Also, we could have a lot of silanose at the external surface. And this is not desired, especially for catalysis, because coke formation starts at the places where are the silanose. Therefore, during the last year, also we focus on the healing of all these defects which are existing at the external surface, but also in the bulk of the nanocrystals. We were able to heal the defects in MFI nanozeolites via introducing tungsten. And the first proof that tungsten was introduced in the framework of MFI zeolite is provided from the X-ray diffraction, where we have seen the splitting of the peaks once the tungsten is introduced, and this is due to the change from orthorhombic to a monoclinic cell. This has been observed before once aluminium was introduced in MFI type zeolite. But in order to prove that our materials do not have any defects, also we perform silicon NMR spectroscopy, and here in red you could see only the Q4 species which are measured for tungsten-containing zeolite. From the CP mass, you could see a flat line confirming that there are no any silanose in the tungsten-containing zeolites. While in the pure siliceous form, we could see abundant amount of Q3 and Q2. Another proof that we do not have any silanose at the surface, as well as nest defects, is provided by the IR spectroscopy. The two blue lines on the bottom correspond to tungsten-containing zeolite. We do not have any signature of silanol nest or isolated external or internal silanol groups, while in pure silicalite 1 prior calcination, we could see very clearly the two bands, and one of them is disappearing after calcination. Very recently, also, we succeeded in the preparation of atomically dispersed molybdenum within MFI nanozeolite, and we prove that this molybdenum is located in the framework in tetrahedral position, and again, this material is silanol-free. In order to understand whether we have a homogeneous distribution of this molybdenum in the structure, also we perform phosphorus NMR, where as a probe molecule we use trimethyl phosphane oxide, and we were very happy to see a peak at 45, which is corresponding to the TMPO on the framework molybdenum acid sites. And also we have seen that the peak which is attributed to the Physisorb TMPO is shifted considerably in comparison to a sample which was prepared via ion exchange. This shifting is also a signature for changing of hydrophobicity, and also we could see that the ion exchange sample has another peak at 50 ppm, which corresponds to silanose, while the atomically dispersed molybdenum introduced directly in the MFI framework does not contain this peak. Up to now, I show you several examples how zeolite nanocrystals could be synthesized via organic and inorganic structural directing agents, but also we've been interested in the post-synthesis modification of these nanocrystals, And under post-synthesis modification, we consider the incorporation of metal and semiconducting clusters in the pores. These metals usually are introduced in cationic form, but then under different treatment, either chemical treatment or plasma gamma irradiation microwave treatment, we've been able to reduce these cations to metals. The first example is on the nano-sized zeolite with LTL type structure, stabilized in colloidal suspension, containing copper 2+, and under chemical treatment with hydrazine, we've been able to find the conditions where we could stabilize only copper 1 or copper 0. Also, this process was followed with in situ UV spectroscopy. Another advantage of using zeolite nanoparticles is the possibility to explore new properties of well-known metals. For example, silver stabilizes in mesoporous matrix due to the size would exhibit plasmonic effect. But in our case, we've been able to put these silver nanoparticles in the sodalite cage of EMT-type zeolite, and as a result, we have seen that these particles are luminescent. Also, we are considering different applications of zeolites, but due to the short time, I will not be talking about catalysis, gas adsorption, but I will mostly focus on the advanced application of these nanocrystals. Before using them, we have to think about different immobilization or formation of 2- or 3-dimensional constructs. And here are given some examples how we could immobilize zeolite nanoparticles as thin films or as 3-dimensional bodies, and all these techniques have been well described in the past. Zeolite have been used for preparation of selective chemical sensors, and these zeolites could be applied either as primary element of the sensor or as a secondary element. In the past, we've been interested in the preparation of thin films via spin coating method because spin coating allows to cover any surface and not to destroy the support. Via using spin coating, we've been able to prepare exhaust sensors for exhaust gases, but currently we are interested in holographic sensors where the zeolite nanoparticles are doped in a holographic polymer and the color change depending on the adsorption of different analytes. Also, we are now involved in a project related with multi-output sensors where the reading is not only frequency but also its color change and etc. Zeolite nanoparticles also are used for medical purposes, and here are listed 3 of the applications. The first one is related with the use of zeolite nanoparticles as a carrier for oxygen and CO2, and to be able to deliver these gases, especially in the places where oxygen is needed. Also, zeolites doped with different metals are used against escape microorganisms, and those microorganisms are of particular concern, especially for hospitals, because they could not be treated with the current antibiotics. And the last application is zeolite as selective capturing material for fibrinogen, which is causing cardiovascular diseases. This is only a summary of the use of zeolites as theranostic tool, and the term theranostic tool is bring from our colleagues from a Cicerone team in Caen. Theranostic tools stands for the use of zeolite nanoparticles as a contrast agent for diagnosis, and this is achieved via introducing iron and gadolinium in the pores of the zeolite. But at the same time, these zeolite nanoparticles are used for vectorization therapy, which means chemotherapy compounds or fluorescent imaging compounds could be introduced in the zeolites. Here are given some recent examples on the use of zeolite nanoparticles as MRI constant agent. Zeolites doped with gadolinium were injected in mice, and now we are at the stage of curing monkeys. And these nanoparticles, within 2 minutes, reach the brain tumor, which is a glioblastoma, artificially induced brain tumor. And it's interesting to see that all the zeolite nanoparticles doped with either iron or gadolinium are located in the brain tumor, while the healthy tissues are intact. With this presentation, I try to convince you that the current state of nanozeolite is, we consider, as bright, because we could synthesize nano-sized zeolites with very high crystalline yield, comparable to commercial zeolites. These materials have high stability, they are non-toxic, therefore they are used for medical purposes. And we hope in the future to be able to extend the number of these nanozeolites, to be able to present more than 24. And also, I show you examples on single-site catalysts, which is on the way to commercialization. And we consider many advanced applications, such as cosmetics, nanotechnology, and food additivation. With this, I would like to thank all people who contributed to this work, our dear PhD students, postdocs, and colleagues from LCS, our collaborators from the 3 laboratories within campus Caen. And also I would like to thank for the financial support of our industrial collaborator Total and UOP, ANR, for supporting the industrial chair Nano Clean Energy. And I would like to advertise the new activities between CNRS and China Academy of Science, which are connected via International Associated Laboratory Zeolites. Thank you very much for your kind attention.